My name is Sam Shamburger, and I'm a meteorologist at the Nashville National Weather Service office. Today we're going to talk about oceanic and atmospheric circulations. The oceans cover 71% of the Earth's surface, and it holds 97% of its water. So it's no wonder that the oceans play a significant role in the transfer of heat energy across the planet, which in turn has an effect on our weather and climate. Water is always on the move, and an ocean current is like a giant conveyor belt that moves large amounts of water all the time. The major ocean currents do follow a common set of circular paths, but why does water move in a circular pattern? The Earth's equator receives more direct sunlight compared to the North and South poles. So it's here that the sun heats the water the strongest, while the water closer to the poles is colder. In general, in the northern hemisphere, warm water from the equator is carried northward toward the poles, and cold water from the poles is carried southward towards the equator. Why? Because of the wind. Our Earth is tilted on its axis, and it's because of this tilt in the Earth's rotation around the sun that causes different parts of the planet to be heated differently. This uneven distribution of heating, especially over land and water, is responsible for our complicated atmospheric circulations. But there are three main circulations that exist between the equator and the poles. The first is called the Hadley Cell. To explain the Hadley Cell, remember that the Earth's equator receives more direct sunlight compared to the poles. Just like this means that the ocean waters are warmer at the equator, the air is too. Because warm air is less dense or lighter than cold air, warm air rises. This creates an area of low pressure at the equator. Meanwhile, the cold air at the poles sinks because it is more dense or heavier compared to the warm air. This creates an area of high pressure at each of the Earth's poles. This difference in pressure causes the air to move and circulate. At the surface, air flows from the high pressure towards the low pressure, while higher up in the atmosphere, the air flows towards the high pressure. If it wasn't for the Earth's rotation, we would just have two large Hadley cells, one in each hemisphere. However, because of our planet's rotation, we have to take into consideration the Coriolis Force. The Coriolis Force is a force that affects the way an object moves over something that is rotating. Think of it like this. Can you draw a straight line from the center to the edge of a rotating turntable? Nope. The air is affected in the same way. Because the Earth is rotating, the air cannot move in a straight line. In the northern hemisphere, the air will always be deflected towards the right. It's because of this force that causes the Hadley Cell to stop in the mid-latitudes of the Earth. The second main atmospheric circulation is the Ferrel Cell. The Ferrel Cell actually moves in the opposite direction as the air in the Hadley Cell. The warm air that has traveled north from the equator meets the cold air that has traveled down from the polar regions. As these two air masses meet, the warm air is forced to rise and move back towards the equator. The last main atmospheric circulation is the polar cell. Cold air at the poles sinks, forming areas of high pressure called the polar highs. The polar cell moves this cold air southward. This circulation is the smallest and weakest of the three. Finally, just like we have fast-moving ocean currents, we have fast-moving currents of air in our atmosphere that we call jet streams. In a jet stream, winds will blow from west to east, but where jet stream sets up is dependent on temperature, as jet streams follow the boundaries between cold air and hot air. While there are several different jet streams around the world, there are two main ones that are of particular interest to meteorologists: the subtropical jet stream and the polar jet stream. The subtropical jet stream is located near the boundary of the Hadley and Ferrel circulation cells, while the polar jet stream is located near the boundary of the Ferrel and polar circulation cells. But the actual location of jet streams can be more complex and depend on locations of high and low pressure systems, hot and cold air, and in what season we're in. Jet streams will dip and rise in altitude, split at times, and even disappear and reappear elsewhere. Air and water is always on the move, and it's these complex circulations in both our oceans and our atmosphere that is the main driver in both climate and weather. We hope you enjoyed this educational video on oceanic and atmospheric circulations. Thank you for joining us.